Sponsored by Brilliant. If this hot wire touches the ground wire, the circuit breaker instantly trips. If the hot wire touches the neutral, it also trips. But if we place a lamp between the hot and the neutral, it doesn't trip. When we turn on a light switch, the current flows along one of the two service hot conductors to the property, then down through the electrical meter, then through the main disconnect, and then into the main electrical panel where it connects to one of the hot bus bars. It travels down this bus bar to the circuit breaker, and then along the hot wire to the switch, and then to the light fitting. It then travels back along the neutral wire to the neutral bus bar, and then back to the main disconnect. Then back through the meter and over to the transformer. The circuit is complete, so the light illuminates. Now, I have animated this using DC current as it's easier to visualize, but in reality, we're using alternating current, which moves backwards and forwards like this. If we measure between the hot and the neutral, we should read around 120 volts. The resistance of the lamp limits the current flowing in the circuit, and so only a small current will flow. This is much less than the rating of the circuit breaker, so it will not trip. If the hot wire came into contact with the ground wire, there would be almost no resistance, so an extremely large current would instantly flow. This would exceed the limit of the circuit breaker, and it will automatically trip to protect the wiring in the circuit. But all the other circuits in the property should remain energized. The NEC defines a ground fault as an unintentional connection between an ungrounded conductor and a normally non-current carrying conductor, including enclosures, raceways, equipment, or earth. When the fault occurred, it allowed current to stray from the intended path and traveled along a normally non-current carrying conductor back to the source, in this case through the ground wire. This is therefore a ground fault, and it means we have a serious problem with our circuit. The NEC defines this as an effective ground fault current path because it's intentionally constructed for fault currents to return to source. Ground faults occur when the hot touches the metal surface of a switch or an outlet, or if it touches the metal electrical box. It happens when a nail or screw is driven through the cable and connects the hot and ground wires, or when a liquid enters the electrical box and provides a passage to ground. Or maybe the insulation of the wire in a device has been damaged and the current flows through the metal case to ground. Regardless of the cause, if we try to reset the breaker, it will instantly trip again. If the fault occurs from a plug-in device, we can just unplug this and the breaker should reset. We then need to repair or replace that device. If the fault occurs from the fixed wiring within the walls, then we need to check the connections to ensure they are all properly fixed and dry. If that doesn't solve the problem, we need to work our way along the circuit, disconnecting sections until the breaker allows the reset. We then know that the fault must occur somewhere in the disconnected section. We can use the continuity function on a multimeter to confirm whether it's in the fixed wiring or within the fixture, as there should be no continuity between the hot and ground. The reason the breaker trips is because the wires will increase in temperature any time current flows through them. This is normal, it happens every time we turn on a device or a light. But if the wire becomes too hot, then the insulation will deteriorate. This will expose the conductors and potentially cause a fire or present an electric shock risk. You may have noticed that there is also a path current can take from the ground rod of the main disconnect to the ground rod of the transformer. This path has a much higher resistance or impedance, so it's far easier for the fault current to take the low impedance path through the service neutral directly back to the transformer. Current can take this route, but the NEC doesn't consider this an effective ground fault path. If we consider a fault where the hot touches the metal case, then the current can flow through the case to reach the ground bus bar, and from here it can reach the main bonding jumper in the main disconnect and get back to the transformer. This completes the circuit and allows the breaker to trip. The raceway between the main panel and the main disconnect is often PVC, so if the ground wire was disconnected at the main disconnect, the circuit isn't complete so the breaker won't trip and all metal parts will become energized. However, if a metal raceway was used, then the current could still reach the main bonding jumper and complete the circuit. If the ground wire was connected, but the service neutral was disconnected, then the only path current can take is through the ground rod to reach the transformer. But because the resistance is so high, the current probably won't be enough to trip the breaker, and the metal parts will become energized. If the neutral bus bar was also bonded in the main panel by mistake, then the ground fault current can travel along the ground wire, but it can also travel through the case and then also along the neutral wire, and if a metal conduit has been used, it can also flow through the conduit. So we have 3 parallel paths for fault current. We don't want that. That's why in this particular system, we do not bond in the main panel. However, older systems without the external main disconnect will be bonded in the main panel. We have covered that in a previous video. If we consider a fault where an outlet or a switch is in a plastic box and the ground wire has been disconnected, then when the hot wire touches the metal surface, there is no way to complete the circuit and the metal surface just becomes electrified. If someone was to touch this, then they can become part of the circuit and current can flow straight through them and find a route back to the main panel. Because the body has such a high resistance, a small but potentially fatal current can flow through them, which might not be enough to trip the circuit breaker. Additionally, if the neutral wire was damaged and it came into contact with a grounded surface or a ground wire, current can flow along the ground wire back to the panel, but this will not trip the breaker because the load is providing resistance. So the current won't exceed the limit of the breaker and it will continue as normal. However, we can use GFCI breakers, outlets, and plug-in devices which will prevent most of these faults. GFCI protection is now required in most parts of the home by the NEC. The GFCI breaker has this coiled neutral wire built in. This breaker fits into the panel as normal, but the circuit neutral will now connect into the neutral terminal on the breaker, and the pigtail will then connect into the neutral bus bar. With this design, the current now flows through the breaker on the hot wire, through the circuit, and then back to the breaker via the neutral wire. It passes through the breaker and into the neutral bus bar, then back to the source. Under normal operation, the current on the hot wire should be the same as the current on the neutral wire, so the breaker will remain active. But during a ground fault, some or all of the current is returning on the ground wire, so the current on the neutral wire is lower than the current on the hot wire. The breaker will realize this and instantly trip if the threshold is exceeded. With the circuit breaker version, all parts of the connected circuit are protected, and anything you plug into the outlets are also protected. So, an exposed neutral ground fault would trip the breaker, and touching an energized part while grounded should also trip the breaker. With the GFCI outlets, anything you plug into the device is protected, and all the outlets downstream are also protected. But nothing upstream is protected. So, an exposed neutral ground fault after this point would trip the outlet. But if the same fault occurred before the outlet, it wouldn't offer protection. Touching an energized part while grounded after the outlet should trip the outlet, but not if it happens before the outlet. Now, a short circuit occurs when the hot and neutral come into contact. There is little to no resistance in these wires, so an extremely large current will instantly flow and trip the breaker. The NEC defines a short circuit as an abnormal connection of low impedance between two or more points of different potential. During a short circuit, the current remains within the intended route. It just took a shortcut to get there. If the hot touched the ground wire, this is also a short, but current has traveled along a normally non-current carrying conductor, which means it's a ground fault. Short circuits can happen if a lamp cord is crushed, creating a path between the two wires, or if a nail is driven into a cable, hitting the hot and neutral wires. Maybe a screwdriver accidentally connects across the hot and neutral in the circuit. However, if a nail is driven into just the hot wire, it will not trip the breaker. The nail just becomes electrified. The resistance of the nail might cause it to become hot when the circuit is in use, or it might create an arc. An electric arc forms when electricity travels through air between two conductors. When a switch flips or a breaker trips, an arc can briefly form between the contacts as they open. But this isn't really a fault. An arc fault is unintended. For example, if a wire is cut or broken, an arc can form between the conductor. If the wire is pulled from the terminal, it can also arc. If the terminal on a switch or outlet is loose, it can also create an arc. If the insulation on a wire is damaged, an arc can form between the conductors. So we have both series arc faults as well as parallel arc faults. The arc is incredibly hot. It damages metal surfaces, it can even weld them together, and it can easily create a fire. So the NEC requires AFCI protection to be installed on certain circuits. AFCI breakers and outlets are used to provide protection. There are different types which are used for different circuits, but the device contains a circuit board which monitors for the telltale signs of an arc fault occurring, and it will then trip if it detects one. Now, electrical engineering is difficult and it requires a lot of complex maths, but our sponsor Brilliant is where you learn by doing. There's so many new courses, but I really enjoyed their new vectors course. The graphics and interactions just make it so easy to visualize each step, and it was extra help if I needed it. Brilliant has thousands of interactive lessons in maths, data analysis, programming, and AI. All the key skills you need to become a brilliant engineer. They even have an app for on-the-go learning, making it easy to build your critical thinking skills through problem solving, not memorizing. Each lesson is filled with hands-on problem solving that lets you play with concepts. I think you'll really enjoy this too. So you can try everything Brilliant has to offer for free for 30 days. Just visit brilliant.org/theengineeringmindset or scan the QR code. You'll also get 20% off an annual premium subscription. Do check them out, links down below. Hey, I'd just like to give a huge shout out to our incredible Patreon and channel members. Thank you so much for supporting us. And if you'd like to see your name here, along with priority access to our content and behind the scenes footage, links down below for how to join.